How cool is that? These are two multimeters, and one of them is actually the one that I use on my channel all the time. I got a second one, and you'll understand why in just a few moments. Now, these two multimeters are very cheap. They're around 30 to 40 US dollars, and they're quite popular as far as I know. But what always bugged me is that when I measure something, I have to point a camera on the LCD display. And you already see that, well, you have some reflections sometimes. And yeah, it's just not nice to work with them. So I was wondering if it's possible to have this multimeter transmit data. Now let's see what happens when I power this one on. This is the new one. Okay, you see the display. Nice, but you also see that I have the reflections here. Okay, let's leave this on. Now let's power on this one. How cool is that? Let me power this off. This is no longer interesting. So I have a display in the top left corner, and this is completely wireless. This multimeter is not attached. There is no OCR going on. This is wirelessly transferring data, but not through a serial communication that comes out of the multimeter chip, because as we will see in a moment, this was not possible. Long story short, I'm actually reading the LCD screen data and transmit it to OBS. Now, let's measure first a few things, and then we deep dive into how you can get this for yourself. There is a GitHub repository, completely open source, for you to rebuild if you want to have data extracted from a cheap multimeter that is 30 to 40 US dollars. So I have two leads here. Let's leave the multimeter here in the corner. Let's first measure voltages. I have a 9-volt battery here. Black goes to negative and red goes to positive. And oh, this battery is quite weak, but you can see the measurement shows up in the top left corner. Now, how about capacitance? And plus and minus. And we get 984. Here we go. So it's 1000 microfarad. Okay, so here's our capacitor. Is it actually true? What is this? Yeah, this is a 16-volt, 1000 microfarad. Let's measure some resistances. I have two resistors here. This is the one. And we have, this is a 47 ohm resistor. And here's another one. I don't know which resistance this one has. 0.33 mega ohms. Now, if I want to have this display in the top left corner a little bit differently, I can increase how big the reading is. Or I can change the theme. So I have, I think, over 12 different themes for this multimeter display. There are some transparent ones, a dark one and a light one. Yeah, and there are many other themes that you can pick from. So for now, let's actually go with a classic view. So this is basically exactly how our multimeter looks like. But now we have a multimeter screen in OBS. And this is just a browser source, by the way. This is not a complicated plugin that had to be written. This is just a browser source. Let's do one last one. Here is the continuity test. And let's have a look at the beeper on the top bar. It lights up when the beep tone is there. So I'm capturing all of this from inside the multimeter. I'll get to the components in a moment, but this is the project I've been working on for about a month now. And why does it take so long? Well, I had to write a complete firmware for whatever devices I'm using. And I can show you how this firmware looks like. So you have seen the home button here. If we press the home button, we get to the dashboard. And the dashboard here, now you see already the name as well, AirMeter is going to be the central place where all your multimeters show up. Yes, multimeters. Later on, we hopefully have 2 meters appear here and you can pick which one to display. The response time is, in this case right now, 300 milliseconds approximately. This is the delay. Why 300 milliseconds? You can go to meter configuration and you can pick your refresh rate. And yeah, this is it. Now there are 2 more things that I fix in this video that have nothing to do with wireless communication, but with the LCD backlight. And for this, I have to turn down the light a little bit here that we see it better. Okay, so now we have low light. I hope it's visible. So let's turn on both multimeters and switch on the backlight. Yeah, you almost can't see it because this is using rechargeable batteries. Now, if I power this one on, you can definitely see that there is a backlight on. Sorry for the reflection, but yeah, you can see that there is a difference. This is the fixed version, and that you see that I'm not making this up. I'll take out now the batteries from here. These are rechargeable batteries. And in here, I have exactly the same batteries, but I'll put these aside now. And put this battery compartment in the old multimeter. Let's power it on. And let's see what happens when I switch on the backlight. There you go. You can definitely see that there is a difference. So yeah, this is what this video will be all about. Now, before we jump into my failed attempt trying to get this data out, let me first show you what we will need as components today. This is the receiver side. This is an ESP32C3. It has a small antenna mod that I've seen online. Sometimes the small antenna, that's that red chip here, that SMD chip, is good enough. Sometimes it's not. So I noticed that this one does improve the Wi-Fi signal. This module contains the web server that you've seen, the dashboard of the firmware, the meter itself. This one takes care of everything. So this one is also the one that connects to your Wi-Fi. There is a full Wi-Fi setup procedure integrated. This comes all with a firmware, and I'll show you how to flash this from your browser with a press of a button later. Now here is an interesting other part. This is an HC12 module. It's wired up here and, well, taped together that it doesn't easily fall out. This is a wireless transceiver. It can send and receive data. And we have one of these also inside the multimeter. But inside the multimeter, there are a few more components. So this one I'm using to receive the information from the multimeter. And then it's processed by the ESP32C3. Now the multimeter, this one here is the new one. If you open it, luckily, we have a lot of space everywhere. So there is a lot of empty space in that multimeter. Now let's have a look at the modified version. And then I explain what we need on the sender side, basically on the multimeter side. Yeah, that is a lot more packed, isn't it? So again, here we already have seen this. There is an HC12 module as well. There's just a little bit connectors here. This is just to hold it in place because I don't want it to fly around inside the multimeter. So here on the very top, we can see an RP2040 Zero. This is a microcontroller that is reading the screen data, and you can see that there is actually a PCB that is hooking up to these pads with these half-cut vias or connector pads on the side. So they go all around on this side, and this is to read the 19 signal lines that go to the LCD screen. Because as it will turn out, this chip does not emit serial data. The only other component here is a 3.3 volt boost converter, because all of these modules operate at 3.3 volts. So that is why we need this boost converter here. And I'm taking it and also feed the backlight. This is something that I always wanted to fix. And here is the fix. So this PCB solves this problem. That is why I have a small pad routed here that can be connected with a wire to the backlight supply. Yeah, and that is pretty much it. And obviously the great part is that this multimeter is pretty empty inside. So we can easily slide all of this and there is no resistance whatsoever. Everything is nicely contained. And then when I power on this multimeter, we're immediately getting the readings. Let's build one of them. Now you have seen the custom PCB, and of course this PCB was fabricated by PCBWay. For this project I needed castellated holes, and you can see them here at the edge of the PCB. These ones sit around the epoxy blob that you have seen and connect to the pads directly, so we don't have to wire all these pads to the PCB. But PCBWay doesn't just fabricate PCBs. They also do CNC machining, 3D printing, sheet metal fabrication, and injection molding. And 3D printing might actually be one of the next projects, maybe not done by me because I have never done anything with 3D printing, but it would be cool to get this into a nice 3D printed housing. So if you're an expert in 3D printing, maybe you can design a housing for these two microcontrollers and contribute to this project. The custom PCB for this project obviously is at PCBWay's shared project space, and of course all the other projects that you have seen on my channel. During this month, PCBWay is celebrating their 12th anniversary, which means you can benefit from discounts on premium solder mask colors, coupons, and win prizes by participating in the minigames PCBWay has on their website. Links to PCBWay.com, their anniversary celebration, and the PCB you need for this project are in the video description. And in the next part, we look at what I thought would be an easy way to extract information from the multimeter, which failed. But I want to include it anyway because it led me to the solution, what is AirMeter today. What we are trying to do today is to get out the serial data that this chip is sending via UART. So there is a possibility to get serial data out of this chip, but it is configured that it doesn't do it at the moment. And the configuration is in this chip. This 8-pin chip is basically just a simple storage chip. It's the 24C02. This chip holds, I think, 256 bytes. And there is a configuration stored in it that disables the serial output. We want to enable it. I tried to read the information off this chip using my programmer, but unfortunately in-circuit programming or reading the data led to overcurrent protection. Now unfortunately this chip is soldered using non-leaded solder and it's not really nice for desoldering or then later on resoldering, so I will just remove it for now, as much solder as possible. And then we use some low melt solder to get the chip off. Read. We got the data. We have to go for FA and we have to set the second bit to active. So let's see where FA is. So this is at CC at the moment. We should enable the second bit or bit number 1. This one apparently is enabling serial communication. So we have to add 2 in hex to enable bit number 1. So let's just add 2. And now you see bit number 1 is enabled. So our new value is CE instead of CC. Oh, and by the way, there is something else you can do with this multimeter. What really annoys me is when I switch on the backlight and it turns off after a certain time. I have never timed it, but it is way too short. And it is very frustrating if it turns off the backlight. Apparently at FC, which is this byte, we can modify for how long the backlight is on. So 78 seems to be 120 seconds. So let's quickly try this. So we are still in hexadecimal. 78 in decimal is exactly 120. So we can set this one to 00, and I believe this then keeps the backlight on indefinitely. Let's change this too while we are here. So our new values are CE, and in here we just write 00. And that's it. Now let's program this chip. Oh, look at this. Done. So this is it. Let's put the chip back on the multimeter and see if it still works. And okay, that looks good. Let's see if our backlight is still working. Yes. And now the question is, does it switch off after 120 seconds? Okay, we passed definitely 2 minutes right now. The backlight is still on. That is fascinating because this was always a feature that really bugged me. I think this is fixed. So chances are very high that we also enable serial communication of the chip that is under the epoxy blob. We just need to figure out now which pin it is. Don't you love a good plot twist? Well, here is one. I developed the entire solution based on the multimeter I purchased 8 years ago. This is the one. This one I just got a week ago or something, and I wanted to use this to show you how I came up with this solution. But as it turns out, there is a significant difference. But it may make this solution all the more valuable. And we will get to this. So let's figure out what the UART pin is doing on both multimeters. Because we know now it's pin 20, and pin 20 sits here in the top left corner, pin 4 from the top. I set up my oscilloscope. Let's probe pin 4 from the top. This is pin 20, and this should be responsible for UART communication. I already changed the bit on the EEPROM here, so technically it should emit data. 1, 2, 3, 4. This is pin number 4 from the top. And it's dead silent. Let me move to a adjacent pin. So let's move one down. Here is definitely a difference on that pad. I go one up. Nothing. And I go one up again. Now I think it's pin 19. And we have data again, or at least there's a voltage difference. So pin 20 is completely dead. This is the meter I had trying to figure out how I can get data out of this. Now here's a new one. 1, 2, 3, 4. Okay, and well, it seems to be connected now. This isn't the case with the old meter. The old meter was purchased 8 years ago. This is something new. But on this meter, I didn't enable the flag in the firmware. It could be that we could read the data directly from the chip on this meter, but not on the old one. That is a little bit frustrating, but at the same time, when I think of it, I have developed a universal solution, which works for both meters. So maybe this is actually a benefit. Now, before I go back to the oscilloscope, I want to do one more test, and this is diode mode. Let's put the red probe on ground, and let's probe pin. Let's start probing pins from the top. I know this is hard to see, but okay, we'll just go one by one. So this is pin, the first pin from the top. This is the buzzer. Then there is another pin, pin number 2, pin number 3 from the top, and pin number 4. Well, pin number 4 is dead. And that is why I came to the conclusion that this multimeter does not connect pin 20 to this pad internally under the epoxy blob. So I was completely locked out. This was the meter I had to work with. Now let's flip these quickly around. I'm again in diode mode, And let's put this red probe on ground. 1, 2, 3, and pin 4 is connected this time. So we definitely have a connection here, which wasn't the case on the old meter. So they changed this. Now, of course, I could read the data probably now from the chip directly, and all my project is basically for nothing. No, it's not. And I'll show you later why. So I had the issue that my multimeter did not expose the UART pin. It simply is not connected from the epoxy blob, and I cannot make a connection. So I had to come up with something else. And the solution was to just read the data directly that is sent to the LCD screen. And these are all these traces that go to the top here. These are 19 different traces, but we have 60 LCD symbols. And how this works is using a multiplexed display. So we are reusing some of these lines for multiple symbols. And how this works was fascinating to discover. Now, if you look at the numbers 60 and 19, they may seem completely unrelated. However, if you split 19 into 15 plus 4, suddenly it becomes logical, because 15 times 4 is 60. And this is the physical layout of how this LCD works and how the DTM0660, the chip under this epoxy blob, works. So the information is transferred using these 19 lines in a 4 times 15 configuration. And this 4 times 15 means we have 4 COM lines and 15 SEG lines. This is just how they are labeled on the screen. And we can probe those and see how they are transmitting data. So the multimeter is on now. When I push the battery pack to the terminals, it should power on. And we will start with the first COM line. So COM 0, this is the 7th pin from the top. I know the duty cycle of this signal is 2 milliseconds. And I want to get a clear picture here. So let's take the 7th pin from the top. Yes, this is pin 7 from the top, and this is COM 0. And you can see that we have 4 different voltage levels. We have 0 volts. This is the dip down to the very bottom. Then we have 1 volt, 2 volts, and the tallest one is 3 volts. So let's see how COM 1 looks like. I just move my meter up 1. It looks very similar. And the next one looks also very similar and very similar. So the COM lines, they do look absolutely identical. Okay, let's move to the first SEG line. Oh, interesting. So again, we have 4 voltage levels, 0, 1, 2, and 3. And we have a nice staircase pattern. Oh, here's something different. So we are alternating between volt 1 and 2, never touching 3 or 0. I'll explain this in a moment what that means. Same for this one. Then we have another segment here. Okay, it does the same thing. Actually, let's see what we're displaying on the screen. That would be interesting. So we are using millivolts. We are in the millivolt reading, but we are changing rapidly back and forth with the numbers. So we have seen these ones, but then you come across something like this, and they are changing. This information encodes what is shown on the LCD screen. Just want to show you the different patterns that we can read here. So this one here is jumping. We see all sort of signals here. We see the staircase, we see the towers between 0 and 3 volts. And then sometimes we have the oscillation between 1 and 2 volts only. Okay. Let's see if we can see another pattern. Well, here, this we have seen before. Here's one that looks a little bit different. So yeah, this is the protocol, the encoding of the screen data. How can we make sense of this? So the COM lines still look more or less the same, what we have seen before. They look like they are following a specific pattern. So it looks like our COM lines define a timing signal, whereas these one dance around the COM lines, encoding the information that is shown on the screen. Now there's one more thing. There's also the beeper. Here's the first pin on the top. This is the beeper. This is also something I'm capturing. So it's an alternating signal going up and down. So this is the beeper. I'm capturing this signal as well. So what are these signals exactly, and why are they so different, and how is the data encoded in those? And this was really fascinating to research and figure out. An LCD like this excites the crystals inside the display with a voltage to show up. The problem with these crystals is that if you would just apply DC voltage, let's say 3 volts, you would damage the crystals in it. To avoid this, we have to rapidly change between a high voltage and a low voltage. In our case, it is 0 and 3 volts. A segment on the display will only show up if the corresponding COM and seg line have the highest potential difference, meaning the voltage difference is 3 volts. It doesn't matter if the COM line is at 3 volts and the seg line is at 0, or the COM line is at 0 and the seg line is at 3 volts. The important part is the voltage difference. And if you have a segment that is oscillating between 1 and 2 volts, it simply doesn't show up. It also doesn't show up if you're oscillating between 0 and 2 volts or 3 and 1 volts. It has to be 0 to 3. And the voltage has to alternate because otherwise we would physically damage the LCD screen. So the solution would be to figure out when a COM line goes high to 3 volts and which of the seg lines are 0. Because that means whichever segment this pair is controlling should be on. So COM at 3, segment at 0. And we have 15 seg lines, so I can get 15 bits at a time. And then we do the same thing for COM1, COM2, and COM3. So what I assume is that COM0 to 3, they all take turns which one is at 3 volts. They should never be at 3 volts altogether. And we have seen from the duty cycle, it is every 2 milliseconds. So this is what I thought will work, reading the screen. But the next part was, how would I know which COM and seg line pair controls which segment on the LCD screen? Well, that was interesting to figure out as well. And we'll have a look at this now. Now we need to figure out which segments on the display are controlled by which COM and seg signals. We have 4 COM signals and 15 seg signals. So I devised something here with the ESP32. I already wired it up and programmed the ESP32. This is the code I used. Basically, I'm using 2 lines that simulate the alternating voltage that we need to drive the display. What I'm hoping is that we can see each individual segment on the display. So yeah, then I guess let's try to fire this up. These copper wires, they are shielded, so even if they touch, there should not be any short circuit. And here is a power bank that is powering the ESP32. This is my probe. I have to hold it on one of the contacts, the seg lines. The COM wire is now attached to COM0, so this is permanent. And now I have to probe each individual seg line. And hopefully when I turn it around, we'll see exactly which segment lights up. So let's power up this ESP32. Okay, code is running. We have a flashing LED. Now let's see what happens. Okay, this project went way out of line. So I know that we have segment 0 on pin number 3 from the top. So 1, 2, 3. And let's see if we get something on the screen. Oh! Okay. It's the M. So COM0 and seg0 control the letter M. Let's take the second one. The ohm symbol. Segment 3. Diode? No, hold. Hold. So there are some others that are lighting up a little bit, but not that much. We can clearly see hold is active. Okay, this was 4, I think. What is this one here now? Oh, Now we have the first segment of our digits, the 7-segment displays. So this is the next one. We can decode the entire thing. Here. No, I lost it. We have only a few more to go. This one. Relative. This one. APO. And this one. Auto. Oh, my finger covered it. Okay, so I think these were all the signals that I need. This one here is the last one. I think that, yeah, auto. Okay, so we decoded the first COM line by probing all seg lines, and we could figure out each individual segment. How cool is that? With this little ESP32 that is actually going to be the receiver, the decoder of what this multimeter is going to send. So this ESP32 will take the bit sequence and turns it into a very nice looking LCD screen, digital LCD screen. Okay, I'll continue with the other ones now, but it's just so fascinating to reverse engineer and debug and dig deeper into this multimeter. We will get there. Next, I want to prepare the multimeter for the HC12 module, and the best way I could come up with is to use one of these pin headers and the connector here that is glued onto the PCB of the multimeter, and then I can just plug this in. All the cables will go to this side, and then it will just hold this in place inside the multimeter. This is the only reason why I have this connector. There is nothing else to it. Here is the perfect spot for adding this connector. Now you see that there is an issue with all these pads that are exposed, so we need to cover them. You can use Kapton tape. This is definitely possible as well, or any other tape for that matter. It's just, I want to make sure we are not accidentally shorting something. Okay, then let me put this outside to let the sun cure the solder mask. Our solder mask is cured. Now all we need to do is we need to place our connector. I want to have it like this maybe. All I do is to add some epoxy on this side of the connector. That's it. I'm not doing anything else. It's just on this side. I don't want to put too much under the connector because there are going to be the pins on both sides. So yeah, you have to be careful that you're not closing these holes for later when you plug in the HC12 module. As I said before, this connector is only here to make sure the HC12 sits firmly inside the multimeter and is not loose. Okay, this is it for now. Now let's discuss what we need to do with all these modules. This is the 3.3 volt boost converter. I just added a pin header because we have to put this upside down on the custom PCB, which is not yet here. So I have to do this at the very end of the project, but I already prepare everything up front. So this is the 3.3 volt boost converter for later. This is our ESP32C3 SuperMini. I already put a heatsink here at the back as well. And I created again the antenna mod. Now a quick word about this antenna mod. The version online doesn't work for me. The version online solders it exactly like what I did here, but also at this middle section of the mod antenna connects to the SMD antenna. In this case, I get actually no signal at all, or it's worse than just using the SMD antenna that is already on the ESP32. I'm not an expert, however, I did some research and my finding is that this is simply wrong. You just connect one side of the antenna to the side with a white stripe and leave the other side disconnected. This gives a significantly better Wi-Fi signal, at least for me. So let me know in the comments if you know something about this, but this definitely worked, at least for me. Then we have a Raspberry Pi 2040. Now this one may look a little bit scary. Yes, there are some wires, but right now only 2 wires are important, and these are the ones that come out from this side. So first the pin 12 here. This one is the sender side. Information goes out from this to the HC12 module. And then I have these two wires. One connects to pin 17, the other one to pin 20. And I would have to check in the sketch which one is which right now, but one is for receiving the buzzer signal, and the other one is for receiving information from the HC12. There will be a documentation how this has to be wired up. So these two wires are important for our mod, and they are coming out under these pin headers, which you can see how I soldered them. So I left the plastic under the PCB, and it will sit like this on top of the custom PCB. This gives a little bit more clearance, and these two wires, we have to cut them later on. They connect to very tiny pads on the PCB as well. So yeah, it is micro soldering. This is unfortunate because I'm missing two pins. The other two pins here, these are for future expandability. I just add them because once this is sitting on top of the custom PCB, it is very difficult to get off. And then we have the HC12 module. There is not much going on, but we still have to configure it. Now, if you follow along building this, I have to admit that I made a mistake and I assembled this radio module wrongly. You can see that the component side is up. It should actually be down because then it's easier to read the markings, which pin of the Raspberry Pi 2040 Zero goes to which pin on the HC12 module. So if you follow along building this, this is the correct way how to put this together and then also have it nicely fit into the multimeter. Just wanted to say this. Let's continue. I'm going to use this Arduino Uno. This worked well for me, and I have two channels here, so the Uno can interface with two of them. Why? Because then I can verify if communication works, and we'll have a look at this also in a moment. So we are testing if I can send and receive data. So the first one I want to flash is this one because there are amazing online tools. So it's super easy, and I'll show you how you can get AirMeter on this device with just one click of a button through a web interface. The easiest way to flash this is you go to the repository AirMeter on my GitHub page. It's also linked in the video description, and you look for install firmware. Once you press this, you get to this page, and then you just have to connect the ESP32 to your PC. And for me, it already turned green here because I tried this before with exactly this device. So I press install firmware, we'll select the COM port, install AirMeter. Okay, so it's installed. We can close out of this now. And now we need to connect to the AirMeter setup Wi-Fi hotspot. So we can have a look at our Wi-Fi, and you see that the AirMeter setup pops up immediately. So let's connect. The password is AirMeter123. We can now just click on airmeter.local. It will take some time to find it. And here we go. So now it will scan your network for a Wi-Fi, and I'll use this one. Continue. And then you just press connect. And that's it. Now the hotspot will stop, and usually your device will reconnect to your home network. So it should automatically reconnect and find the ESP32 on your home network. We'll see this hopefully now. It should turn green. It's searching for it. And here it is. So open dashboard. And here is our web UI. And you can see your IP address here. This is significantly faster to access than the host name that you've seen here. So I would always continue with the IP address. And that's it. So now the ESP32 is ready for action. We still have to wire up the HC12 module, but this will come later. This one is now completely configured and ready. Now we can disconnect it. So this is done. Next one is the Raspberry Pi 2040. For this device, we need to get the firmware for this microcontroller. So you can get this from the GitHub page as well. Just go to releases and look for the AirMeter RP2040 Zero UF2. And now all we have to do is to connect it to our PC, and hopefully it will show up as a flashable drive. So let's plug it in. And here's a new drive, RPI RP2. And all we have to do is we have to copy this file onto this drive. There you go. And that's it. Drive disappeared, and our Raspberry Pi 2040 is flashed with our firmware. Now we need to take care of this HC12 module. And there are a lot of information out there about this module, but I'm not going to go through the details. I'll only want to mention that if you get modules like this, they are most likely configured in a way that is illegal in most countries. You can read up on this. I'm not going to go into details. However, when I use the Arduino Uno and the sketch that I prepared, which is also on my GitHub, they are programming these modules that they are legal. So yeah, just keep that in mind. So I have two modules here. This is the one that is connected to my ESP32, and we want to check if bidirectional communication works. You see module A, the one that isn't programmed, in the bottom right corner. So let's plug this in. We have to change. No, so here's the Arduino. And here's the program running already. So with this program, we can read the configuration of both modules. We can compare the settings and check for compatibility. We can program them individually. We can program both simultaneously. And finally, you can run a communication test that basically sends bidirectional signals from those two modules. And it will also detect issues if you have a faulty module. So let's first read the information. So option 1 is reading the configuration of module A. This is our new module. Let's see what it's configured as. And we can see that we have a baud rate 9600. It is still on channel 1, so this would not work. And this means we're using the most power to send data, and we're in FU3 mode. So we need to change these definitely. Let's see how module B looks like. Module B also baud rate 9600. We have channel 3. I think you can go up to channel 4 without needing a license in most countries. So this is what I mentioned before. So we can just program module A, which is option 4. So let's program module A, and that's it. Module A is configured now. Now we can see if they are compatible. I should have done this before, but now it should say they are compatible. Let's see. Configuration. So configuration settings match. Perfect. So let's run the advanced test and see if we can actually communicate. Okay. It looks like FU4 does not work. I will look into this, but important for me is the link here. Link A to B is passing in FU1, and link B to A is also passing. So these two are working correctly. Okay, now we are in good shape. The only thing that's missing is the custom PCB. I still have to wait for this, but once it's here, we'll get this assembled as quickly as possible. And finally, the two items that I have been waiting for finally arrived. One is this IC. These are comparators. I'll explain what they do when I'm assembling it. And here are the PCBs. So let's see how these PCBs look like. Yeah, this is what I was looking for. So we have the PCBs, we have the logic IC. Let's build one of these PCBs. Then we will add our Raspberry Pi on top of it. So this is going to sit on top of here. And then all of this goes into the multimeter, and we have to solder these castellated holes around our IC with epoxy blob. Okay, let's not waste more time and let's build one of these PCBs. I haven't tested this yet, so that is why I'll not mention too many values. All I can say is that the ones with a bar in the center, these capacitors are all 100 nanofarad caps. So I'll pin these pads now, because then I can just place the components and use my Hoda station to attach them to the board. It's easier than soldering every component individually. And for smaller PCBs like this, I don't think there is a need for a stencil. It doesn't take much time. Now I need to place these resistors here, and these 4 resistors build 2 voltage dividers. One is for 2.5 to 2.7 volts, and the other one is for 0.5 volts approximately. The reason for these 2 voltage dividers is to give reference voltages to our comparator chips. So if you remember from what we said before, that we have to figure out when a COM line goes high. In our case, it's 3 volts. And we do this by using a threshold, in this case 2.5 volts. So whenever the line goes above 2.5 volts, these comparators will output a logical 1. If it's below 2.5 volts, it will output a logical 0. So these 2 resistors on the left, they are creating the around 2.5 volts threshold. And the ones on the right, these ones are for generating 0.5 volts. And this is to figure out which seg line is at 0 volts. So this is the whole dance around this staircase that we have seen on the oscilloscope, which segments on the LCD display are visible. Okay. So now this one. Okay. Next, we have to solder our comparators. And as I explained before, these ones are responsible to generate a logical 1 or a logical 0 from the staircase pattern we have seen on the oscilloscope. This is all that these chips are going to do for us, but it's a very important task. So this project was so interesting because I learned so much about different signals, different chips like these comparator chips, how to read a multiplexed display, how to use an ESP32 as well as the Raspberry Pi 2040 Zero and these HC12 radio modules. And then of course writing the firmware was also a little bit of a challenge. So the board is clean and I checked already all the connections. They look good. Our board is ready for the Raspberry Pi 2040. And here it is. So this one will sit like this on top of this PCB. We have to connect these pins to these pads all around, and that means basically you can see the wires that come out underneath. We need to solder those as well, and this is the first thing I want to solder because if I make a mistake somewhere, I can still fix it. This is pin 17 and this is pin 20. So 17, it's the first pin here. You can see I marked it a little bit with black paint. So here is pin number 17. And pin number 17 is for our RX pin. And pin 20 is for the buzzer. Oh, now they're crossing. That's not nice. I think I have to change these pads in another revision when it goes online. These wires are coated, so there shouldn't be a problem, but I still don't want them to touch. Let's tin these. It is a lot of micro soldering, and actually I'm going to change my tip right now after I tin these pads. Okay, so now let's get the first wire attached. This is something you need a little bit patience. Okay, so first one is attached. Now let's take the second wire and do the same thing. Okay. So yeah, I may change the orientation of these pads, but you can see now both are attached. Now all that is left is we have to solder all those pins around, and you can see that pin 12 is excluded because this is a pin that connects to the HC12 module. Let's do pin by pin. And I changed back to my bigger solder tip because it just has more thermal mass and it makes nicer solder connections for these pins. So yeah, this is one of the longest videos I've ever made, but there is a lot going on in this project, so I wanted to show every single step to make sure that I don't have to answer too many questions, so you can see the full process, how I made it. All these ones solder quite nicely. And these connect to our screen pins, so the COM and the SEC signals. This is what these pins are used for. This is all that is happening. They are reading the values from the LCD screen. So the multimeter doesn't even know that we're tapping into the data that it's producing. Okay, and that's it. And now we're finally here to connect this PCB to these pads around the multimeter chip. And you can see that these pins, these castellated holes, line up very nicely. So now we just need to put some flux. Maybe make a nice connection. Let's start with the first castellated holes that are going to connect to this multimeter. Okay. And let's get the last one here in place too. The 2 points that are furthest apart from each other, and the rest should basically match. I think this is good enough. And then we should be done. Ah, no, we also have to put the backlight in place, right? We fix this too. Now, with this multimeter, I didn't make the modification in the EEPROM to leave the backlight on. I'm not going to do this. You can read up. There is a very good documentation what you can do with the EEPROM, so you will find more configuration settings. If you want to modify the default behavior of your multimeter a little bit, you can just take off this EEPROM chip, change a few bits, and yeah, get maybe the functionality that you wanted. Okay, so this looks good. Alignment is okay. So you can let me know in the comments what you think, how difficult this project is in terms of soldering it, or also in the other sense, like, did you understand everything that I was explaining? I mean, for me, this was not that I had any prior knowledge to what awaits me, but yeah, this was basically what the end result was. Okay. So this is in place. Oh, we also need our, where is it? Here. 3.3 volt boost converter. And because I didn't have space here, I'm deciding to just put it like this on top of it. Actually, we have to turn it that way because V in is here on the right, and you can see this here on the PCB as well. This is voltage out. So voltage out is this one here. So I have to place it that way on top of these pads. Yeah, this will also be a hacked together solution. We have to make sure that we leave a little bit of a gap between this screw hole and the PCB, because otherwise we will run into clearance issues when we put the cover on top of the multimeter. But yeah, that should be fine. Okay, I think this is good. Now we have enough clearance. Let me just try this quickly. Yes, it does close. No issues whatsoever. Okay, and finally, let's also get our voltage in properly soldered. And this is our boost converter. I took the liberty to already wire up the connector and more or less finish everything except of the backlight. You don't have to watch me soldering wires, I believe. So here is the HC12 module. Luckily at the back we can see which pin is what. So I'll just leave it here and we can look at the colors. So the set pin we are not going to use, so this is not connected at all. Then we have TX. TX is the white color wire. And this goes into RX on our PCB. This is what I wanted to clarify. So TX, what does it mean? TX means data is coming out of the HC12 module. It is transmitting. So it's transmitting data, and on this side we are reading it. So on the RP2040, this needs to connect to an RX pin. So this is talking, this is listening. This wire is responsible for listening. And the RX pin, which is yellow, so this is where the HC12 module is listening, and that is why we need to connect to a TX pin on our Raspberry Pi 2040. So this one is talking, and this one is listening, and then it's basically transmitting it over the Wi-Fi wireless radio. And then we have black for ground and red for VCC. So VCC, I'm connecting here directly on the bottom of our boost converter here. So we have 3.3 volts and we have ground, and this goes then to our HC12 module. Now I'll still add a capacitor. Nice. So I'll still add a capacitor here between these two pins. This is ground and voltage out, so 3.3 volts. I'll place here a 100 nanofarad capacitor. But now let's have a look quickly at our backlight. So I already connected the wire, and here is the wire that goes into the backlight. All we have to do is we have to cut this trace that comes from this capacitor. Yes, unfortunately, we have to cut the trace and go to our backlight. At the beginning of this video, I showed you that if you're using rechargeable batteries, the backlight is very, very weak. And this is unfortunate. With this solution, while we already have a boost converter on this board, we could just fix this problem. So then we have the possibility to run this multimeter with rechargeable batteries. And the backlight is bright, which is great. So I think this is definitely cut now. Now I don't have a multimeter to check. Well, I have one, but they're both disassembled right now. I have no multimeters. Yeah, that is definitely cut. That looks like a voodoo card surviving the scrapyard, to be honest. This is what I sometimes see. Okay. And this should fix our backlight issue. And we are finally done. Both of these multimeters are modified now. So this one here was already running before. This is the new one. The only thing I added is this 100 nanofarad capacitor on the 3.3 volt line output. So we have a little bit of a storage there. And otherwise, yeah, you see there's a little difference. There is another capacitor here, which we hopefully no longer need in this revision. That is why there's a new revision of the PCB that I was waiting for. And yeah, I think we can power it on and see if both of them register in AirMeter now. Yeah, let's do the first test. Let's see if we can close this. Perfect. Also this one here. Nice. Yeah, so sorry for the reflection, but this is what we have to deal with right now. Let's power on our original meter. So this is the original one that already worked. And here it is. So it appears on the screen. Yeah, here it is. So yeah, it does send information. So that's great. Now the question is, does this meter appear? So our original one here is on channel 1. You can see this here. A new meter should always appear on channel 0. So let's see if we get a new multimeter on channel 0 now. It's the first time I power this on. I haven't tried this. All this work. Let's see if it works. Yay! We have a unknown meter at channel 0. And we get the data. I mean, we get the screen. Wow, this dial is so much nicer than my old one. But we get all the information. How cool is that? So now we have a second meter at channel 0. So now you can go to meter configuration. You see the old one. You see the new one. So I'll also name this ANENG AN870. This will have the red rubber body, and the channel remains where it is right now. Power saving, yeah, we can switch on power saving, but I also want to switch it to 5 Hertz, and we have it enabled. So let's see if it's saving. Yes, it sent it to channel 0. And we have now 2 different multimeters here. Now the big question is, do they work simultaneously? Because, well, this is another test I haven't been able to do because I only had one multimeter. Okay, and here is a setup with both meters now. So this is my old meter. This is configured on channel 1. By default, if there is a new meter and there is no configuration setting, it is channel 0, and this is the red one. So on the left side, you can see this is AirMeter. Both of these multimeters have registered, and if I power one on, it will turn green, and you can see on the screen now the reading. So let me go to a faster setting. This is changing rapidly. Now let's see what happens when I power on the second meter. Turns green, and we get the reading as well. How cool is that? So let's go to volt reading. Let's just measure a few voltages. So here's my 9.7 volt battery. 9 volt battery, 9.7 volts reading. Let's try the other meter. 9.7. And you can see how the screen is split, and we get the correct reading on the right screen. How cool is that? Okay, you can see that the AirMeter has been upgraded a little bit more. So we see, first of all, we see the meters here. By the way, if you're seeing these delays now, this is because of power saving. So when the meter doesn't change, like when the screen doesn't change, we are not sending data. You can see here this one. Okay, this one looks like it's offline right now. Now it should go back on. Yes, because I saw the one on the screen. So yeah, this is all power saving, trying to not waste battery. That's it. Now, let me talk a little bit about AirMeter. So it has been upgraded since I started this video. First of all, you get a few more options here at the bottom. We have now temperature reading that is lower. If you look at the very beginning of this video, you have seen there were around 60 degrees on the ESP32. And why does it happen? Well, because of the CPU frequency, right? Actually, no. But let's first talk about the CPU frequency anyway. You can utilize the Wi-Fi module on the ESP32 at a frequency of 80. You can clock it further down, but then Wi-Fi wouldn't work anymore. So you can switch between 80 and 160, but honestly for this project, 80 megahertz is enough. I had no issues whatsoever, so just leave it at 80. The temperature dropped because of the Wi-Fi power. So in here right now we're running at eco. This is basically allowing the Wi-Fi module to go to sleep when there is no data being transferred. If you go to max, you immediately see that the temperature is climbing. So yeah, this will go up to 60 degrees. Honestly, for normal operation, I don't see that you will ever need to use max. You can just go to eco and leave it there. Now there is also a diagnostics page if you need to figure out if there is an issue with one of the radios or there is an issue with the Wi-Fi. So if you go in here, let's make this full screen. First of all, you will see a little bit information about your Wi-Fi, how long it takes for the ESP32 to respond. Now this is slow because we are not sending continuous data from our multimeters. If I let both of them send, you will see that this latency is going to be reduced because we are sending data. So this is a smart way of the Wi-Fi module on the ESP32 that is allowing us to save, conserve power, and at the same time reduce temperature. And now in here you can see the 2 meters. So now we have 2 meters active. One is set at 3 updates per second and the other one is at 5 updates per second. And you can see the graph here, how many packets are being sent over 1 second. So you can see how well your connection is. You can see how far they can transmit and so on. And if a meter goes into power saving or doesn't send updates, you will see that the packets are dropping, but they should also recover again. There you go. So yeah, this is the power savings mode. Of course, if you go into meter configuration and you disable power savings, meter configuration. So here, if you disable this, then the multimeters will send data regardless of the screen having changed or not. I also added this last option. This disables communication totally. So for instance, if you don't want to use AirMeter at all for an extended time, you can turn the radio off. What this does is it will disable most of the screen reading on the RP2040, and it will also not send any data over the HC12 module. You can still send information, so the RP2040 can still receive information, but it will not send. So, and if you go here, you'll see the radio is off right now. And yeah, it hasn't been seen for a minute now. When you power it on though, it will send 1 packet because the ESP32 needs to know on which channel this multimeter is and where it can send information to. So you can disable this silent mode or when the radio is off basically. So when I power this on, we'll get 1 packet and here it is. And now it's dead silent again. So you will not receive any information. This is the most power conserving way. Now you will not see anything here because there is no data being sent. Of course, there is so much more about this project, but I can't. The video is long enough. You have seen what it does. You have seen how to build it. If you have questions, send me an email, share your thoughts in the comments. In the video description is the link to the GitHub repository. It contains the Gerber files. It contains the full source code of AirMeter. And yeah, if you want to, you can just go ahead and modify the entire UI, add graphs, add historical data, do whatever you want. I recently implemented zipped HTML content. So basically it can serve now compressed HTML files. Compressed files always have priority. So if you want to modify something, just extract the HTML file from this compressed file, delete the compressed file and just upload always the HTML file. You have 1.2 megabytes still free on this ESP32. So you have plenty of space to extend, modify, alter, and do whatever you want. Yeah, and this is all I have for you today. I hope you enjoyed this project. I hope you learned something. I hope it was entertaining. And I'm really looking forward to hearing from you. What do you think about this? In the end, I want to thank all the people supporting this channel. And if you want to support this channel and maybe also because of this project, you can either head over to Patreon, you can buy me a coffee, there are links in the video description, or you can also become a member here on YouTube. I'd really appreciate it. Thank you so much for your time. I also want to thank PCBWay for sponsoring this video. Of course, this PCB is going to be available over at PCBWay's shared project space. And while you're there, also have a look at my other projects. Now, before we go, does the backlight work? I almost forgot this. This is the old one. This is the new one. So both of them are working. Great. Our mod fully works. Wow, what a project. Well, that's it. Thank you so much for watching, and I will see you in the next videos. Take care and bye-bye.